Okay, in this video we're going to look at how we work out the number of hydrogen NMR environments. We always talk about hydrogen 1 because that's the type of hydrogen that has an odd number of nucleons. Deuterium, which would be hydrogen 2, wouldn't show up on an NMR because it has an even number of nucleons. Okay, so if we start reasonably simple, here we've got methane. Each one of those hydrogens in methane is in the same environment, so that would just have one peak. We look at this one here, this is ethane, CH3, CH3. Those two CH3 groups are equivalent to each other. There's a line of symmetry running down this molecule. Okay? So if I turn the molecule around, you would be able to tell it's still be CH3, CH3. So again, this only has one hydrogen environment. So both these molecules have one hydrogen environment. It's only one peak on a hydrogen NMR graph. Right, if we look at something a little bit more challenging. Here we've got propane. Okay, so propane, the two CH3s are in the same environment. I could flip it around, it'd be the same environment. And the CH2 here is in a different environment. Okay, so those two are the same environment as each other, but this one's a different environment. If you look at the ratio of protons, the area under each peak in hydrogen NMR is proportional to the number of protons, number of hydrogens that it represents. So here we've got 3 plus 3, so we've got 6 in one environment and 2 in the other. So the ratio would be 6 to 2. Obviously 3 to 1. Okay, this one here, each one of these CH3s, each CH3 is bonded to the same carbon here. So although I've drawn it kind of almost rectangular in its display formula, if you imagine it three-dimensional as a tetrahedral shape, these CH3s are all attached to the same carbon in a tetrahedral shape. So they're all equivalent to each other, they all rotate around this carbon. So each one of those CH3s is in the same environment, and then that one hydrogen there is in a different hydrogen environment. So here we have 2 environments, this one, and there's 9 protons there and 1 there, so that'd be a ratio of 9 to 1. We have a look at this one, benzene. In benzene itself, there's just one environment. Okay, so each one of these hydrogens is equivalent to each other. So it's just one peak, one hydrogen environment. When we add this, these hydrogens are different, obviously, and where this differs slightly to carbon NMR is we don't differentiate in benzene the different hydrogens. So there's no hydrogen there, but then there'll be another 5 there. And because the splitting pattern is actually very complicated and beyond the scope of this course, we just look at that as one environment. Okay, I know even though those two are different to those two, in carbon NMR we look at that difference, but in hydrogen we don't. We just say that would be one hydrogen environment there. It's got 1, 2, in the ratio of 3 to 5. Okay, so 3 to 5. If we look at this one, here we've got an ester. The thing about esters is they're not so very symmetrical because of the nature of the ester bond. Okay, so we've got 2 CH3s, but they're not equivalent to each other because if you look at this CH3, it's nearer to that O there, that oxygen there, than that CH3 is. So that's one environment. That's another one. Again, the CH2s are different because this one's bonded directly to an oxygen, this one isn't, and this CH3 is different again. So we've actually got 1, 2, 3, 4 environments. The ratio of hydrogens in those environments would be 3 to 2 to 2 to 3. So we have 3 2, 2, 3. So in that graph, in that spectrum, you would have 4 hydrogen peaks, 4 hydrogen environments, so 4 peaks in the ratio, so the ratio of area underneath the graph would be 3 to 2 to 2 to 3. Okay? So these ratios will be equivalent to the area underneath the peaks.